Dear colleagues and esteemed attendees, it's a great privilege to extend my warmest greetings. I'm engineer Salvatore Polverino, and for our study, among the foremost hazards, in example, urban electromagnetic pollution, unauthorized activities, and electronic warfare (AW), we noticed that they impact software definite radius. We must consider indeed the intersection with the technological and cybersecurity threats in terms of digital erosion for peace posed by the dense RF environments. An example, Rome's Colosseum and Athens' Acropolis. So why Selinunt? The site is located along national borders of Italy and stands as a strategic laboratory site for threat mitigation. The study specifically is characterized by the electric properties in high-resolution synthetic aperture radar (SAR) imaging, which is essential. By understanding how various surfaces reflect, absorb, or scatter radar signals. Highly conductive materials such as metals exhibit strong reflections, making them easily detectable in SAR imagery, reducing the likelihood of conflict and promoting regional stability. As for Italy, in example, the F-35 Lightning stands as one of the cornerstone of modern defense strategies, delivering unparalleled deterrent technological advantages. As a multi-role stealth aircraft, its ability to integrate advanced sensor fusion, network-centric capabilities indeed, and precision strike ones, ensuring superior situational awareness. As, as for the core methods, we observe the conversion of raw SAR data into GIS compatible formats, focusing on calibration, speckle noise reduction, and georeferencing. As for format conversion, SAR and optical image fusion, SAR and LiDAR data fusion and GNSS integration, polarimetric and others, interferometry, stereo SAR, fusion with LiDAR and optical digital elevation models, coherence and amplitude change detection, persistent scatter interferometry in structural changes, multitemporal SAR analysis, and here indeed the software involved. So these are the system level methodologies based on state space representation with a focus on VX works for real-time mission-critical avionics applications, estimating radar cross-section RCS, and integrating signal processing theory. With jamming dynamics and ERP considerations by combining scattering models and power equations. State space equations model, radar propagation, reflection, and RCS under complex EM conditions. As for F-35 multi-sensor systems, it exploits these dynamics for autonomous long-range targeted detection of the electric reflections and ISR optimization. Matrix formulation captures polarization effects and propagation losses, scattering coefficients sigma HH, sigma VV. For F-35, the AS enable 360 degrees threat detection. Eigenvalue, the composition of the permittivity tensor epsilon models, anisotropic media response in radar propagation, coupled with Maxwell's equations and Fourier-based analysis. This supports multispectral sensor fusion for dynamic situational awareness. Inverse permittivity epsilon minus 1 and Green's function gives F govern the propagation of electric fields under complex media. The F-35 APG-81 ASA radar exploits this modeling to enhance ACR resolution, enabling precise imaging across operational contexts. Phase shift and power loss L model spatial resolution and signal attenuation. As for this fusion, ACR, ESM, DAS, and EOTS enable real-time threat detection. So key research constraints include reliance on ACR data, high computational demands, and poor cross-site generalizability. There is also a lack of long-term evaluation, limited AI integration, and insufficient standardization across collaborative frameworks. Future directions include fusing ACR with AO, LiDAR, and GNSS, advancing multiscale RCS analysis, and refining noise reduction. Game theoretic models and reinforcement learning enable ACR system to dynamically avoid jamming by optimizing action policies UAS. Reinforcement-based game theoretic also see ACR, RWRDS, and stealth target detection in contested environments. Kalman filtering enables real-time fusion for ACR, RWR, and DAS data for enhanced target tracking. State updates minimize error covariance, improving detection under dynamic conditions. Kalman filtering tracks ACR, RWR, and DAS estimates under jamming by predicting state evolution and adjusting with noise jammed observations. The gain metrics adapt over time, minimizing estimation error despite interference JK. Fourier-based spectral control models radar signals as ST, enabling isolation of jamming in the frequency domain. System response as S filters interference, supporting resilient signal reconstruction. ACR, hence signal behavior, is modeled through reflection parallel R, attenuation alpha, and backscatter sigma, accounting for the electric properties. Plots show how incident angle and material type in example soil, water, concrete affect energy loss and radar return intensity. The radar return equation PR shows rapid power decay with distance and lower RCS. The stealth targets reduce sigma, shifting curves downward and limiting detection range as visualized in the power distance plot. Multifrequency ACR modeling incorporates the electric effects via reflection coefficient parallel R, gain, and polarizations. As for figure 6, multifrequency ACR also is encoded in matrix S with the electric gain G with a unified ECM model epsilon. Formalizes signal degradation under jamming for countermeasure design. Effective power return PR jammed reflects both signal and jamming contributions across polarizations filtered adaptively via J filtered. Here we outline the core steps of the methodology. First, feature extraction is performed using ORB key points integrated with Kalman models for stable tracking under motion. Next, we conduct data collection, permittivity values, epsilon 1, 2, with Gabor filters, GLCM across HH bands. This methodological section presents the mathematical basis behind SAR detection under noisy conditions we have approached. We model wall and roof scattering of the built environment using permittivity-based reflection terms and wave geometry. The equations define how incident angles, building shape, and the electric properties influence the backscattered signal. Model selection prioritizes accuracy and balance. In parallel to this, the device shown under the F-35 is part of the electro-optical targeting system, EOTS. It enables real-time ground target locking, tracking, and definition in parallel with our methodological framework. Now, the electric properties of surface materials which affect radar cross-section. Key factors include permittivity, surface roughness, correlation length, impacting multi-bounce reflections. Angular dependence 0 to 45 degrees show how incident angles want to affect RCS return, varying with materials like asphalt, concrete, and vegetation. And the low frequency ACR system exploit these variations for penetration. Last instance, magnitude and phase responses, which characterize radar signal interaction with materials, multi-notch filters, isolate specific frequency bands, processing interference of jamming. The ORB key points, our grid cell with a heat map, Lex data, our scattered data quantitative analysis. So the integrated approach combines signal modeling, the electric analysis, and ORB-based feature extraction for a precise differentiation. This methodology supports robust RCS estimation and improves detection reliability in both operational and heritage-sensitive environments. We want to thank you for your important attention, and goodbye.